Alright, chemistry class, let's talk about quantum theory. So, all started back with a German physicist from the 1900s. His name was Max Carl Ernst Ludwig Planck. Most of them just called him Planck. But anyway, he suggested the idea that energy is quantized rather than continuous. So, quantized means it comes in little packets, not that it's like it can come in any variable. So instead of a continuous ramp where you can you could be a half or 1/3 or whatever the way up. You can go any length of the ramp you want, and you're going to gain some height. So it's continuously changing. However, with stairs, it's like the idea of quanta. So you can only absorb a certain amount of energy. So you can take one step or 2 steps or 3 steps or 4 steps or 5 steps, but you can't take a half a step. If you do, you're just going to fall back down. Like if you take 1.5 steps, you're just going to end up here and be like, fall back down. So that's the first general idea. So Planck came up with an equation. Of course, everybody comes up with an equation if they're a physicist. So basically, energy is equal to Planck's constant times the frequency. So handy equation, E equals hv. H is Planck's constant, and it's basically 6.6261 times 10 to the negative 34th joules per second, or joule second. So you might notice it's a really, really small number, times 10 to the negative 34th. It's like a whole lot of zeros before you even get to like the number. So we can't really notice a change in energy that small. Like if you get 1 quanta or 2 quanta of energy, you're not going to notice it. You need like thousands of quanta for us as human beings or animals really to see it. However, for atoms and really small subatomic particles, the difference in one piece of energy or one quanta of energy can have really big effects. He also noticed something called the photoelectric effect. This is how solar-powered lights work, or solar-powered electric generation works. So in the photoelectric effect, electrons are ejected from the surface of a metal when light shines on the metal. Has to be the right type of light. So for each metal, a minimum frequency of light is required. You remember back from the waves and talking about the electromagnetic spectrum, as you increase energy, you increase the frequency, or increase the frequency, increase the energy. So, for example, red light with a low frequency is incapable of releasing electrons from sodium, while violet light with a higher frequency, smaller wavelength, can release electrons from sodium. Interesting fact. So Einstein realized that Planck's idea of quanta could explain the photoelectric effect. So if energy is quantized, it comes in little pieces, then light is quantized. Light is a type of energy. So if light comes in pieces, then different frequencies of light have different amounts of energy. So if the energy of a photon is small, it doesn't give the electron enough energy to then escape. But if the energy of a photon is big enough, it can cause the electron to leave. It gives the energy to the electron, and the electron goes. That's kind of interesting. So then get into some weird stuff. In 1923, Arthur Compton demonstrated that a photon could collide and change the motion of an electron. So light has to have mass. So we're thinking about energy. Energy doesn't have mass, right? But it does. In some weird, freaky way, it does. And then, 1924, a year later, Louis de Broglie reasoned that particles of matter should behave like waves and exhibit a wavelength. He referred to that as matter waves. He really wasn't accepted until it was later proven, but and in fact, every time you move, you have a de Broglie wavelength. So even if you think you're moving in a straight line, you're actually waving back and forth. We don't really necessarily notice that because the wavelength and the mass are inversely proportional. So in order for us to be able to actually observe the wavelength, we have to have a really, really small mass. Really the only time this comes into play in any practical purposes is for electrons. If an electron is moving, that electron is moving in a wave. It's kind of interesting. So, along those lines, we came up with Heisenberg's uncertainty principle. I had to put both Heisenbergs over here. So it says that the position and momentum of a moving object cannot be simultaneously measured and known exactly. So we can't know where a particle is and how fast it's moving or where it's moving, therefore being able to predict where it ends up. Okay, so imagine this. You're in a dark room, shine a flashlight around to find your keys. If you did that with an electron, the light from the flashlight would actually make the electron move in some unpredictable way. So finding it at one point, okay, yeah, well, the electron's over there, doesn't do anything to help you know where it's going or where it will be at some point in the future. Interesting stuff. So that wraps up this one. Ask me if you have any questions in class, and good day.